Welcome. Today we are going to solve a few questions on electrostatics, and we'll begin with the analysis of this chapter with respect to JEE Advanced, right? So you see that in the last 5 years, when you see, on an average, a couple of questions have been asked from this chapter, right? 1 or 2 questions always gets asked, sometimes even 3 questions. And when you talk about mains, at least 1 or 2 questions would be there from electrostatics. But it is not a chapter that you can leave. It's not a chapter that you can take easy, because this is a chapter which forms a base for all other chapters of electrodynamics, and electrodynamics bears a good percentage in the JEE paper. Okay, so let's start our discussion with sort of an easy question. So in this problem, you have a point object which is charged, and there is a horizontal electrical field which will of course apply an electrical force on it, and there's a point when it slides down this hemispherical surface and it loses its contact. Okay, so before arriving at the point where it loses contact, let us discuss about a general point, like what are the forces acting on this thing. So let's say I'm talking about say this point over here at some angle alpha. Okay, this object is, let's say, here. What are the forces at this angle alpha? Okay, so let me draw the FBD over here. Okay, so now you have got a QE force, the force due to the electrical field, and its own weight acting downwards, which is mg acting downwards, mg, and because it is in contact with the surface, you have got a normal reaction as well. So normal reaction is acting like this. Right, it will be acting radially outwards. Okay, now what I'm going to do, I'm going to resolve these forces in the direction of the radius and perpendicular to the direction of the radius, that is in the radial and tangential direction. So I've got mg, and this is the radial direction, right, and this is the direction perpendicular to the radius. And if this angle here is alpha, right, this angle here will also be alpha. So for mg I get this side mg cos alpha, and here I get mg sin alpha. And when I resolve QE, I get, if this angle is alpha, this angle will be 90 minus alpha, and this angle again will be alpha. So QE, if I resolve, I get here QE cos alpha, and perpendicular to that here I'll get QE sin alpha. Okay, now I know all the forces in the tangential direction should add up to a net force which must provide the centripetal force for this motion, right, because it is moving in a circular path on the top of this hemisphere. So let me do that. So I get mg cos alpha minus n minus QE cos sin alpha equal to the centripetal force, which is mv square by capital R. Okay, so this is the expression at a general point. Now I want the expression at a point where it loses contact. And what is so special about the point where it loses contact? The point where it loses contact, n becomes 0. Okay, there's no more normal reaction. So now this expression becomes mg, instead of alpha I'll have theta, mg cos theta minus QE sin theta is equal to mv square upon R. Right? Now I know the value of theta, right? The value of theta which is given to me is equal to sine inverse of 3 by 5, right? That makes sine theta equals to 3 by 5, and if sine theta is 3 by 5, cos theta you can find out to be 4 by 5 from a 3, 4, 5 triangle, right? From a 3, 4, 5 triangle, this angle is theta, then sine theta is 3 by 5, cos theta is 4 by 5. Now this becomes mg times 4 by 5 minus QE times 3 by 5 equals to mv square by R. I have no idea about what this speed is, right? What is this v of mv square by R? Now I need another expression in which I have this speed, so I would have some way to like find this ratio of mg and QE, right? So what can I do? What other expression can I use? I can use the work energy theorem. So if I want to use the work energy theorem, I'll have to see what are the forces acting on it. There is an electrical force and the gravitational force, and how much work they're doing. So let me do that. So if I talk about the electrical force QE, right, the QE force is acting on it like this, and it displaces it till here, till over here, right, till theta. So what is the distance to which it displaces? It displaces this object by this much distance, right? So if this distance is r, this is theta, so this will become r sine theta, right? So QE is a constant force which displaces this object in its own direction by a distance of r sine theta. So I can write this as QE times r sine theta. Okay, that much is the work done by the force QE. Now mg is the force which is acting downwards, right? Mg is acting downwards, and because of that mg, this object gets displaced by this much distance. And how much is this distance? From here to here, right? This is the distance we are interested in. This whole distance is r, right? And if I use this triangle, I can say that this distance over here, this distance is r cos theta. So this will be r minus r cos theta, right? So that will be, and you can see that the object is moving in the direction of the force, so the work done will be positive. So plus mg times of r minus r cos theta will be equal to, this is the net work done, there is no other force. Normal reaction always acts perpendicular, and it is not moving in the perpendicular direction, it is not moving in the radial direction, right? It should be equal to the change in kinetic energy. So initial kinetic energy is 0 and final kinetic energy is half mv square. Okay, I know the value of theta, so I can write this as QE r times of 3 by 5 plus mg r minus r times of 4 by 5 equals to 1 by 2 mv square. Okay, let me call this as equation number 2, and let me call this as equation number 1. Okay, in equation number 1, what I can do is I can multiply this by r, and I can get r over here, right? And now I want to get rid of the speed, right? So I can just divide these two expressions. So what do I get? When I divide this, I get r 4 by 5 r mg from here minus 3 by 5 r QE equals to mv square, and from the other expression I get 3 by 5 QER plus mg r 1 minus 4 by 5 equals to half mv square. Okay, so I'm going to divide this. So let's just divide these two expressions like this. What do I get out of this? So out of this I get this expression. Now what I'm going to do is I'm going to just take this r out and cancel it, right? And I get 4 by 5 mg minus 3 by 5 QE is equal to, and 2 would get here, 2 times of 3 by 5 QE plus 1 by 5 mg. This becomes 4 by 5 mg minus 3 by 5 QE equal to 6 by 5 QE plus 2 by 5 mg, and this comes on this side becomes 2 by 5 mg if I have taken mg on this side and QE on that side. This becomes is equal to 9 by 5 QE, right? So mg by QE, the ratio of the gravitational force to the electrical force, comes out to be 9 by 2, and that is option number A. So in this problem you are given a linear charge density about a ring, and you can see that this density is not constant because it depends on theta, and we are supposed to find out the potential at the center of this ring, right? So how am I going to do this? So what I'm going to do is I'm going to write the potential due to a very small element, and then I'm going to add the potential due to all the elements, because potential is scalar. I can do that. So let me take a small element here at some angle d theta. So at some angle d theta, I take a small element, say dl, right? Now what will be the length of dl? dl will be equal to r times d theta. If r is the radius, let's say, dl will be equal to r times of d theta. Okay, And what will be the charge there? What will be the charge in that small element? The charge will be equal to, GQ is equal to the linear charge density lambda times the length, which is dl. So this can be written equal to the value of lambda is given to you as 2 times of cos theta by 2, right, times dl, which is r times of d theta. So this is the small charge there. And what will be the small potential due to this small charge? The small potential due to this small charge dv will be equal to kq by r, right? K times of q divided by r. So this becomes k times of q is 2 times of cos theta by 2 r d theta divided by r. So r gets cancelled. So this comes out to be 2k cos of theta by 2 times d theta, right? This is the potential. Okay. Now all I have to do is I have to integrate this potential throughout the circle, right? Throughout the circle I'm going to integrate this. So this becomes integration from where to where? From 0 to 2 pi, because the angle you see varies from 0, when the theta goes from 0 to 2 pi, right? So this becomes equal to 2k as a constant comes out. Integration of cos theta by 2 is sin theta by 2. So sin theta by 2 also divided by 1 by 2. Don't forget that. From 0 to 2 pi. 1 by 2 comes over here. This becomes 4k, right? Times of sine of 2 pi by 2 will be sine pi minus sine 0. Right? What is sine pi is 0, sine 0 0. This comes out to be 0. So the answer is a perfect 0. Okay. So the potential at the center of this ring of variable linear charge density is 0. So this is a really interesting question. Here you have a non-conducting disk with a surface charge density of sigma, and there's a charge object which is falling towards its center. Okay, and you're supposed to find out a ratio of h by a, where h is the height from which the object is dropped and a is the radius of this disk. Now the interesting thing is the initial velocity of this object is 0 and the final velocity is also 0. So both of them are 0. Okay. Now what will happen when it falls like that? Okay, so when the object will fall, there will be two forces acting on it. One would be its own weight, which will be trying to pull it downwards. It will be trying to increase its speed, and the other would be the electrical force, which is acting in the upward direction. So that will be trying to decrease its speed, right? So it starts with a 0 speed when the weight is more, or when mg is higher, and then by the time it reaches to the center of the disk, both the forces work out in a way that the net change in its kinetic energy is 0, right? So how would I solve this problem? So the first thing which clicks to me is that the net change in kinetic energy of this object, right, the delta Ke for this particular thing is equal to 0. From work energy theorem, I can say that the net work done, right, the net work done on this must be 0. That means the work done due to gravitation plus the work done due to the electric force must be equal to 0, right? Now what is the work done due to the gravitational force? So gravitational force is a constant force, mg, acting downwards, and the motion is also downwards. So I can say mg, right, that is the gravitational force, times the displacement, which is equal to h, plus the work done by the electrical force. Now electrical force here will be acting in the upward direction and the object is going in the downward direction, right? So the work done because of the electrical force is something I can see, I can tell that it is going to be negative. And the problem is that the electrical force is not constant. So I have to find the work done because of electrical force. I'll have to integrate it and I have to take a small element and do all that thing. There's actually another way to find work in case of electrical forces. Also you can use it for gravitational forces though, which is to use electric potential. And that's why we had come up with the idea of electric potential, because it becomes very easy to do calculations. So the work done by the field on a charge when it moves from a potential of VA to VB, right? If a charge moves from a point, let's say A to B, the work done by the field, right? So the work done can be by the force, by the agent. It can also be by the field. So because of the field, the work done is minus Q times V final minus V initial. So in this case, it will be minus Q times VB minus VA. Okay, a quick mnemonic. By the agent, it is Q times of V final minus V initial. This is the way I remember it. Because of the field, it will be negative of that. Okay, so this will be minus Q times of V final will be VO and V initial is VP, right? And that must be equal to 0, which tells us that MGH must be equal to Q VO minus VP, right? Now my job is to find what this VO and what this VP is, right? I don't know the expression for the electrical potential due to a disk. And in case you know the formula, balle you can solve the problem. But if you don't know the formula, then you'll have to find that formula, right? And to find that formula, you'll have to do some kind of integration. Now, how can I do that? Now, when I look at a disk, the first thing I remember is a ring, right? When you have a ring, the electric potential at any point on the ring at a distance of, let's say, x from the ring is very easy to find out, because see, all those charges that are which are there on the ring are equidistant from that point, right? And so whenever charges are equidistant from a point, you can simply add all the charges, right? So KQ by R is the formula for a point charge. You can just make that formula K sigma Q by R when the charges are equidistant from a point. So K times of sigma Q is Q, capital Q, let's say that's a charge in the ring, divided by the distance from that point, which will be under root of R square plus X square. And that's the formula of the potential due to a ring, KQ by R square plus root over R square plus X square, right? You're getting my point, right? It's easy because all the charges are at this equidistant from that point. But in the case of a disk, it is not the case. All the charges are not equidistant from the point where some random point where we want to find the potential. Now what do we do? So the logical thing is to break this disk in different rings, right? So if I take a ring, an element, a ring-like element of infinitesimal length or infinitesimal thickness, you can say, and let's say the thickness is dr and it is at some radius small r from there, right? Now what would be the charge in this ring? So the dq, the amount of charge on this ring will be how much? So let's find that. So the dq, the amount of charge, that will be equal to the surface charge density, which is sigma, right, times the area of that ring. So the circumference of that ring is 2 pi times of r, right, and the thickness of this ring is dr. So this will be the total charge which will be in that ring, okay? And this is the charge on this ring. And what will be the potential which will be created by that ring at any point, say at some point x? What will that be? That dV will be equal to, right, k times of the q, which is sigma 2 pi r dr, okay, divided by kq by r, that is the distance. And what is the distance here? In this case, the distance of the ring is, this is x and that is small r, so distance will be r square plus x square whole to the power or under root of that, okay? So this is the potential due to that ring. Now I have to find a potential due to the disk, and so I have to integrate it, right? Now here the variable of integration is r, and r is the radius of that ring, okay? And the radius varies from where to where? From 0 to a, right? So from 0 to a, I'm going to integrate this. So this guy comes out to be k, which is 1 pi 4 pi epsilon naught times sigma and times 2 pi, these are all constants, integration of r dr upon r square plus x square under root, okay? And this runs from 0 to a, okay? Now how I'm going to integrate this? See, integration of this is very easy. R square plus x square, you can take it to be some other, like you can take it to be equal to L square or something, and then you can differentiate that, and then you'll get, like, you have an R term sitting on the numerator. So the integration is not very difficult in this case, right? Another interesting thing here is that x here is not, although x is a variable, but x is not the variable of integration. The variable of integration here is r. X is a fixed point where we are trying to find out the potential. Okay, although usually x is the variable point, but here it is not. So when you integrate this, you get this to be equal to sigma by 2 epsilon naught, right? Because this 2 pi becomes 2 sigma by 2 epsilon naught root over r square plus x square going from 0 to a. So I encourage you to try to do this integration on your own. Okay, now this will be equal to sigma by 2 epsilon naught root over r square plus and this r is actually will become a, right, when you plug it in. So this will become root over a square plus x square minus x. So this is the potential due to a disk at a point on its axis. Now you see that it took us like a few minutes to arrive at this expression. So you're encouraged, if you're appearing for JEE Advanced, to remember this formula, because it's great to have the philosophy that you don't have to remember anything, but a few things if you have on the back of your head, it becomes easier. It will save you time, and saving time is also one of the objectives of JEE paper. Okay, now what? I have found the potential expression. So now if I write the if I want to find the potential at O, my VO will be what? The value of x at O is 0, right? So that will become sigma by 2 epsilon naught times A. And what will be the potential at P? That will become sigma by 2 epsilon naught root over A square plus h square, because here x, the value of x is equal to h, minus h. So these are the two values of VO and VP that we have found. Now what? Now we have to use this expression which we have found initially, right? mgh is equal to q times of VO minus VP. Now we have gotten VO, we have got VP. Let's plug it in and let's see what we get. So I get this expression, mgh is equal to this. I've just substituted VO and VP. Now what do I get? So from here I can do is my GH will become equal to Q sigma by 2 epsilon naught times M. This M has come over here, times of A minus root over A square plus H square plus H. Okay, and it is given to me that Q by M, that ratio is given in the problem, right? That ratio is 4 epsilon naught G by sigma. So I can replace this Q by M with 4 epsilon naught G by sigma. And when I do that, I get this to be equal to GH is equal to 2G. So this whole thing becomes 2G, right? 2G times of A minus root over A square plus H square plus H. Okay, and this G and G would also get cancelled. So you get H by 2 is equal to A plus H, right? A plus H minus root over A square plus H square, and that becomes what would that become? So this will become this H. If I bring this over here, I get root over A square plus H square equal to A plus H by 2, and I'm going to square both the sides to get rid of the square root. I'm going to square both the sides. When I square both the sides, I get A square plus H square is equal to A square plus H square by 4 plus AH. Okay, and that becomes what? A square and A square gets cancelled. This cuts with this and becomes 3H square by 4. So you have got 3H square by 4 equal to this A by H. So A into H. H gets cancelled with the square. You get 3H by 4 is equal to A. And our question, you remember, asked us to find the ratio 3H by A. So 3H by A will be equal to a neat little 4. And that's the answer to this problem. So in this question, we have a cube of side A, which is placed in a coordinate system. You're given that the nearest side is at a distance A. So this here is A, all right. And there's an electric field. Now electric field value in the y direction and z direction is 0. But in the x direction, it is equal to beta x to the power of 1 by 2. It means it is changing with x. Right? When x was 0, there was no electric field, and as x is increasing, the electric field is increasing. And I have to find a charge enclosed in this cube. Every time I get a question where I hear the word charge enclosed, the only thing that clicks to my mind is electric flux. So what I'm going to do is I'm going to find the electric flux over this cube, and then going to use the Gauss law to find the charge enclosed. Now, when I look at this surface, right, this top surface over here, I know that the electric field is going to be like this, right? So the electric field is going to be grazing through that surface. So if I take a normal on that surface, if I take a normal like this, then the angle between the electric field and the normal is going to be 90 degree. And you know that the flux is equal to E dot dA integration, right? This is the general formula for finding flux. So all the elements are going to be perpendicular, so the dot product will be 0. So here, see, anytime a field grazes through a surface, the flux contribution because of that field is 0. So the flux on this surface is going to be 0. Similarly, on this surface, the flux is going to be 0. And that is going to be true for the front surface as well, because even for the front surface, the electric field is actually grazing through like that, right? So that is 0. And even for the back surface, it is 0. So we have got only two surfaces left, the surfaces on the side. So we have got this surface over here, right, and this surface over here, where there will be some flux contribution. And what will be the flux contribution on this surface? Now when you look at this surface, right, so this surface is at a fixed value of x. All the points on this surface is at a fixed value of x, right? It means that the electric field at any point on this surface is constant. And what is that electric field? The value of x there is equal to A, right? So the electric field at this point is equal to beta times of A to the power of 1 by 2, right? That's the electric field. And the area vector, the normal, will be in this direction, is always in a direction which is in the direction of outward normal, we call it, right? So that if you have a closed surface, it is away from the closeness, it is away from that closed part, right? So it is called an outward normal. And the electric field is in the other direction, the electric field is in this direction. So the dot product will be cos, you will get cos pi in the dot product, and cos pi is equal to -1. So the flux contribution due to this first side surface will be beta A square, that is the electric field, times the area of the surface, which is A square times -1. Okay, because electric field is constant, I reduce this formula to E dot A and simply get E dot A here. Okay, otherwise the general formula is this, you have to remember that. Now what is the flux because of the other surface, on the other surface here, right? Here is your other surface. What is the flux there? So now there also, when you see the value of x, the value of x here is constant, right? So when the value of x is constant, electric field is going to be constant, because electric field only is varying with x. And what is the value of electric field there? Beta times of the value of x there is 2a. So beta times of 2a to the power of 1 by 2. Okay. And what is the normal vector? The normal, the area vector is outward normal, like this, right? So it will be outside. But it is in the direction of electric field now, because electric field is also in the x direction, outward normal is also in the x direction. The dot product is going to be, cos 0, which is the cos 0 value that is going to be 1. So dot product will be equal to this electric field times its area, which is A square. So what is the net flux? Because flux is a scalar quantity, I can add them. So phi1 plus phi2, when I add, what do I get? I get beta A to the power of 1 by 2 A square, this is negative, plus beta 2A to the power of 1 by 2 times A square. So I can take out certain things from here. I get -1 plus root 2 times of beta A to the power of 2 and A to the power of 1 by 2, both are there, so it becomes A to the power of 5 by 2. So this becomes equal to root 2 minus 1 beta A to the power of 5 by 2. Okay, and this is equal to the charge enclosed by epsilon naught. Okay, And so the charge enclosed will be epsilon naught times this value. So when you multiply this value with epsilon naught, you get the charge enclosed. And so the option C is the right answer. So in this problem, you have a uniform magnetic field and the magnitude is given as 325 volts per meter. Okay, and we have got a motion of a charge from A to B, a unit positive charge, right? And the coordinates of A is given to you as -2, -3. Coordinate of B is given to you as 4, 5. What will be the coordinates of this point? Let's call it C. So what will be the coordinates of C? The x coordinate will be -2 and the y coordinate will be 5. So -2, 5 will be the coordinates of the point C. Okay. Now I have to find the work done in moving it from A to B. I know that, see, whenever you are moving a charge in a direction, in an electric field in a direction which is perpendicular to the electric field, the net work done is 0, because the force will act in a direction in the direction of the electric field, and the motion is perpendicular, the displacement is perpendicular. So F dot D, right, is going to be 0, right? So there will be no work done. So in this case, the work that you will have to do in moving it from C to B, from here to here, will be 0. So I have to, like, don't worry about that. So all I have to worry about is the work done in moving it from A to C. Okay, and that work done, we have a simple formula for that. A work done by the agent is equal to Q times V final minus V initial. So V final is VC minus VA. Okay, or I can simply write this in this case Q times of delta V. What will be the delta V between C and A? Okay, now we have to find that. Now the electric field here is constant. Electric field value is 325 volts per meter. And how much is the displacement here? How much is the distance between these 2 points? This much is 5 and this is 3. That becomes how much? 5 plus 3 is 8. So the L value is 8. I know that delta V is equal to E times of L, or E times of delta L, right? So E is 325 times delta L is 8. So that becomes 2600 volts. That is the change in the potential, and when you multiply it with charge, which is a unit positive charge, so the charge value is 1 coulomb, the work done you get equal to 2600 joules. So in case you don't remember this formula, you can use it like the normal work done formula, right? So what you can say is that, let's say there's a charge here and the electric field is in the downward direction, so the charge is feeling a force in the downward direction. The force this charge is feeling is in the downward direction, but we are asking the work done in moving it from A to C. So it is not the electrical force which is moving it, it is the agent who is moving it. So the agent will be applying a force in the opposite direction. So agent will apply a force in the upward direction, right? So the motion is in the direction of the agent. The force which the agent will be applying will be the charge, which is 1 times the electrical field, which is 325. So the force will be 325, constant force, for how much displacement? A linear displacement of 8. So 325 into 8 will give you 2600 joules. That's also a way to solve this problem.
For more videos and live lectures on the JEE, click on the subscribe button now.